The attendance is kind of low today, but anyway. Uh, right. So today we are going to talk about the containers in STL, which we couldn't cover last class. So in this today I'll cover basically whatever I didn't cover in detail in iterators, and then I'll move on to containers. And also I made some mistakes last class, and I'll also just correct them today. Uh, so what are iterators? Uh, Iterators are objects that provide a way for us to traverse over a container without having to worry how the container is implemented. So basically, uh, sorry about that. Basically, we have a container and we want to go over all the elements in it, but we don't know how the container is implemented. Say, for example, set. Set is internally implemented as a binary search tree, but we don't know how to go over a binary search tree, and we don't care also. We just want to go over the element. That's it. And iterators are a convenient abstraction that allow us to do that. Now, this is a bit of theory that is not really that relevant for competitive programming, but it's good to know. So, iterators are defined in terms of the operations they support. For example, a pointer to an array, the kind of pointer that you have probably learnt in your C class in college, that kind of pointer can be incremented. You know, you can increment a operator plus plus, you can decrement it by minus minus, you can move it to any point in the array. You can just do, if you have say A, then you can do A plus 5, and that will take you 5 elements forward. And you can do minus 5, you can move to any point in the array in constant time. And you can also read what data is pointed to by the pointer by just dereferencing the pointer by star A, right? So this pointer satisfies the requirements of this thing called a legacy random access iterator. Uh, and additionally, actually, if you look at it, if you look at this table right here, uh, sorry, let me just right. So if you see right here, it also satisfies the requirements of contiguous storage because an array is stored in memory contiguously, as you know. So it's also a legacy contiguous iterator besides being legacy a random access iterator. So basically, a pointer can be used anywhere. They expect you to give a legacy random access iterator. This much detail is not required, but I thought it would be good if you knew what is like what are the different classes of iterator, because uh, as we go on to see the various containers, we'll see that some of them have random access and some of them don't have random access. Those that have random access typically belong to this class, and those that don't have random access belong to one of these three classes. Okay, so we'll see that. Uh, so now let's just look at some common operations and iterators. First of all, this is an example of how you declare a vector. We'll see this again. But what is important is how are we going to declare an iterator on this vector? Okay, so we have the type of the vector right here. We have this vector int, right? So now if you want to declare an iterator on this vector, what we'll do is we'll write this, we'll write the type of this vector, then we'll use this scope resolution operator, which are these two colons, and then we'll just write iterator. Okay, that is all we need to do to define an iterator on this vector. And then there is the name of the iterator, and we are going to assign it to something called begin. Okay, so vector dot begin. Okay, so now this begin is a member function which returns an iterator to the start of this vector. So vec.begin is basically a pointer to this one right here. Okay. So now the operations that we're going to look at, one is dereferencing an iterator. I mean, this one should be pretty obvious. If we dereference the iterator, he will just get output 1 because the iterator is pointing to 1 and we dereference this iterator and we get the value that is pointed to, and that is 1. Then we can increment an iterator. We increment it. Now this iterator will move one step forward and now it will point at 2. Now if we ask for what value is there, we'll get 2. Now we can decrement it and now it will go back. So it'll go back by 1 element. And now if we again ask it, it'll print 1. And it turns out that the iterator that is defined on a vector, that is also a random access iterator. So this thing right here, this is random access. Okay. And that means we can increment or decrement it by any amount we want. We can do it equals it plus 3. And now it will move forward by 3 places, 1, 2, 3. And now it is going to be pointing at 4. So now if we ask for it, it will print 4. Okay. And the one more operation is if we want to see if 2 iterators on the same container point to the same element. Note that it doesn't really make sense to compare 2 iterators on different containers since they are two different things. Okay. But inside the same container, you can see whether 2 iterators are pointing to, say, the same element. Okay. So the way you do that is just obvious. It's obvious. You just use the equality operator and equality operator. Equal or not equals to. Okay. And this final statement right here is an example of looping over a container using a for loop. Okay. And we are going to use iterators. So we have our iterator here. And now this iterator we are going to set again to vec.begin, which means it's pointing here at this one. While this iterator is not equals to the end, the past the end iterator. This vec.end, this returns something called past the end iterator. So okay, so last class, I think I may have said that vector does not store its elements contiguously. That is wrong. So vector stores its elements like arrays. Okay. So in vector, it's all stored contiguously. So it's stored like this in memory, 1, 2, 3, 4, 5. Okay. So now just imagine this block right here after 5. Okay. These are all blocks of memory, as you know, 4 bytes because it's an int. So this is begin. Okay. And this is end. So while this is not equals to end, we will print whatever is at 8 and then we will increment it. Right. So first we will print 1. Then we are going to increment it since it's not equals to end. So now it was here, now it is here. And now we are going to print 2. Then it's going to come to 3, print 3, come to 4, print 4, 5. And then next when it increments, it will reach end. And now it is equals to end. Right. So, well, so now the for loop will terminate and end of program. Okay, so any questions up to here? No questions? Well, okay. So I'm assuming everyone understood. One more thing is that there is these two iterators, which is begin and end, and there are also two things called reverse iterators. Now, these reverse iterators, basically what they do is they traverse the array backwards. That's it. Nothing else. It's just going to traverse it instead of front, it's going to traverse from back. So now these two reverse iterators, so this is our array.
Is this complex screen duration? Okay.
So these two reverse iterators are called R begin and R end for reverse begin and reverse end. So R begin points at the last element since it's traversing backwards, and R end points right here again past the end iterator, but this time instead of being after the end of the array, it's before the beginning of the array. Okay. So if you increment this iterator, so if you do this, if you have say a iterator equals to R begin, say vec dot R begin, if you have this, and if you do it plus plus, instead of moving like this, it will not move like this, it will move backwards. Okay, so it will move like this. So it's just very convenient to have this because I mean the whole point of these containers is their size may change, right? So if their size changes, of course you can get their size with the member function called size, but it's just a lot more convenient to just be able to directly access from the end. Okay, we will see that. Okay, and now this is something that's just really useful. Okay, so this is something called automatic type deduction. Okay, so basically that just means you don't have to write the type of the variable anymore. The compiler will reduce it for you. Uh, and this is achieved by something using auto. Okay, this is a keyword that's exclusive to, I mean, it's not, it was there in C, but it's used for a different purpose. In C++, this auto keyword, what it basically tells is that we are not going to say what type it is, the compiler will deduce it for us from based on what it is being assigned. Okay, so let's look at these two first. So here, this is a variable x and we have assigned it 5. Okay, now without any suffixes like say ll, if we wrote 5ll or I don't know 5u. Okay, so without all these suffixes, by default this is assumed to be int. So this auto right here, this will be replaced by the compiler to say int. Okay, and this y right here, this is a double, right? Because there's a 1.0, right? Because it is a real number, so it is automatically assumed by the compiler to be double, and this will be replaced by this will be replaced by this. We didn't have to write the type. Where this is most useful is when we are writing these iterators. Okay, so if you go back here, you see that we had to put this whole type and then we have to write iterator. Now imagine you have a much more complicated types like say map, pair, int, and if you have this monstrosity right here, are you going to write it every time you make an iterator? That would be kind of a waste of time, right? So instead of writing this whole thing and then iterator, what we'll just do is we'll write auto and we'll assign it, and then the compiler will automatically deduce that yeah, okay, this thing is a vector, an iterator for a vector, right? So this is where it's useful. Just instead of writing this whole thing, we can just write auto, and the compiler will do the work of filling in this thing for us. Okay, and I will be using this kind of syntax a lot in the following code examples. So make sure you understand what I'm saying here. Okay. So any questions?
Normally it is not encouraged. Okay.
No questions? I mean, okay. So I'm going to assume everyone understood. And I'll move on to the next slide. Okay, so now we are going to begin our discussion on containers, and these are the containers that we're going to discuss, all of these. So first we'll start with the most common data structure that you'll use, and that is vector, and which is basically array with variable size. Okay, and it has a lot of helpful member functions. Okay, so first let's see how you declare a vector. Okay, so there are several different ways of declaring a vector. So what is common among all of them is you write vector. Okay, you write vector, then you write the data type, you write the data type, and then you write the name of the vector. This is common for all of them. Okay, this kind of syntax right here. For the others, for the first one, what we have is this basically tells us that we have a vector of ints with name vec, and that is initialized with these elements in this order. So this is basic. This means that vec is equals to 2, 3, 5, 4, 1. So it's basically the same as declaring an integer array, say int r is equals to this thing right here. Okay. Instead of writing, like, yeah. So this kind of syntax is, hello, someone unmuted. Okay, so this syntax right here is the same as array, right? Because here you will use curly braces, right? And then you will write down the element. So this thing is same here, and you will probably have noticed that I omitted the equals sign here, and that is okay because C++ accepts this kind of syntax without an equal sign. Okay, so like you don't have to write like r like 5 equals 1 2 3 4 5. You don't have to write this. If you omit this equal sign and just write this is also okay in C++. Uh, the next one is another kind of syntax where we used a constructor. Okay, so I think you guys have probably not covered. I mean, you probably don't know about classes. I mean, unless you are coming from, say, Java, you probably know about what is class, constructor, destructor. But anyway, so the point is that this kind of this syntax, this is the size. Okay, this is the size of the vector. So what this is telling us is that this is a vector of size 6. But we have not set its elements to be equal to anything. Okay, they are just you can just say they are kind of garbage values. Okay, it's the same as declaring int r 6. Okay, we don't know what is in the array. We assume it's just garbage. Okay, now this one instead tells us that this is a vector of size 6 where all the elements are 4. Okay. So this 4ll, this ll thing just means that it's a long. Okay, it's just a suffix. Even if you remove the ll, it would automatically be typecasted to long. But yeah, so this is vector of size 6 and all elements, all elements equals to 4. This is what it says. And this last one is an example of a multidimensional vector. Okay, so just like how you can have multidimensional arrays with say R5, 20. So you know this is a matrix of 5 rows and 20 columns. So similarly, you can do the same thing with vector, but here you will have to use kind of a nested definition. So there is a vector and this vector contains some vectors. Okay. Now each vector inside here contains an int. So we have a vector of vectors. Okay. And now here we are saying that the size of this is 3. So there are 3 vectors in this vector. Okay, so 3. This is a vector. This is a vector. This is a vector of int. And then we are going to say what all the elements are. Okay, so each element is a vector of ints of size 3. Okay, so each of these is a vector of size 3, and each of these, again, nested definition here. So inside this we are going to write the size is 3 and every element is 2. So basically every element is 2. Okay, so what this has created in effect, this has created a matrix of size of 3 columns and 3 rows with all elements equals to 2. So any questions here?
Like if we want to define three different elements, then what should we give the input?
As in 3 different elements, as in?
Like you gave to get all the three elements as to you gave 3 comma 2, right?
Yeah.
Like if we need to give 2 3 1, then is it possible
Okay,
to give?
so yeah, that you cannot do. For that, you will have to individually go and assign using a for loop.
Okay.
Yeah. Now, vector has some important member functions. Again, I will remind here that if you want to use member functions, you have to first put name of the vector, say vec. Then you have to put this dot, which is member access operator. And then you'll have to use the name of this function and then any arguments to this function. This is the syntax for using member functions. You should remember this. Right? This is important. And these member functions, there is actually, this is in any of the examples that I'll give, the member functions that I'll write are not a complete list. There is a vast list of member functions and you can see it on CPP reference. Okay, so I mean, most of the member functions you'll probably not require anyway. So I've just given the most important one that you'll probably be using all the time. So the first two are pushback and popback. So what these two do is pushback basically, okay, here I made another mistake last class. Last class, I remembered that I said that there is pushback, push front, and popback, pop front. That is not true for vector. Push front and pop front are defined for our deck, which is double-ended queue, and we'll see that at the end. Okay. So vector only has pushback and popback. Okay. If you want to insert anywhere else, you'll have to use insert. Okay. And you'll probably not be using this. You'll probably only be using pushback and popback. So pushback, what it does, this is both of these are constant time. Okay. So they insert an element at the end of the vector, or they remove an element from the end of the vector. Okay. Size just tells you what is the size of the vector. Like if you use, say, like right here, if you say vec3 dot size, then you will get the output as 6. Okay, this just tells you what is the size of the vector. Empty tells you if the vector is empty, if there are no elements in the vector. So if you used vec2, if you said vec2 dot empty, then you would get output as true. Yes, this vector is empty. We have not put anything in it. We have just declared it. Okay. Begin, rbegin, and end, rend, I already explained before. These return iterators to the beginning and end of the array. Right. So beginning, as in if you use begin and end, it will be first to last. And if you use rbegin and rend, it will be last to first. Forward iterator and reverse iterator. Okay. Then clear just empties the array. If I mean this vector. So if there was anything in the vector, it just removes everything that was in it. And now it will be a fresh vector. Okay, so nothing in it. Okay. So clear is also done. Resize. What resize does is it basically, well, I mean, it should be obvious, it resizes the vector. So if I said, if I had vec2 and I did then vec2 dot resize 10, then now this vec2 will have a size of 10. Okay. But all the elements inside will be garbage because we didn't assign them anything. Okay. So vec2.resize, what it does is it changes the size of the vector. And again, resize can be used to decrease the size also. So if we did vec3.resize and then we did say 3, then before we had this 6 elements, and now all of these will be removed and these will stay intact. These will stay intact. These will stay as they are. So now we'll have vector 235. I mean, 235. Sorry, not 235. Wait. Huh? Oh, sorry. I should have put one more. Oh, who cares? So we had 2, 3, 5, 1, 4, 6. Then 1, 4, 6 are now gone because we resized it to be of size 3 instead of size 6. So the last 3 elements are gone now. This is what resize does. Insert and erase, what they do is so you pass an iterator to them. You pass iterator, and whatever element is at the position pointed to by the iterator, it will be removed if you use erase. And if you use insert, an element will be inserted before or after, like I think after the given iterator. Okay. So well, basically you will not be using insert and erase most of the time. Most of the time you will only be using pushback, popback, because anyway you will probably be you'll know the size of the vector beforehand most of the time. Okay, and even if you don't, you'll use pushback to add on to the end. But just good to know. There are sometimes there is a use for erase, like mm, okay, a use for erase would be, say, if you want to get the unique elements in a vector, then there is a way to do it using this STL function called unique. And when you use this unique, you also have to erase everything at the end, and there you will have an expression like unique, then end, and then you will just erase all these. Any questions?
Nope.
No?
For
Okay.
erase, if I put an iterator in a means a middle iterator somewhere in the middle, will
Yeah.
it shift the array means shift the later part of the vector forward? I mean,
No,
for
like
example,
yeah. So okay. So if you have say again, let me take 2, 3, 5, 1, 4, 6, and then you say v dot erase, and then you say this is begin 1, 2, so v dot begin plus 2. This will erase the 5. Okay, so this will just erase this 5. But everything right here is going to be just moved forward automatically. So now you will have just 2, 3, 1, 4, 6, and the size of the container will be 5. Okay. You don't have to move these elements by yourself. The erase function will automatically do that for you. Does
so
that
it
answer
works
it?
on
Yeah.
time complexity O
Will
of
it
n, right?
be will it be constant time complexity then?
It will not. If
Will not.
you,
Yeah.
it will not. So if you are erasing from anywhere inside the array, it will be the time complexity is O of uh, number of uh, elements after uh, deleted position. So uh, so what it does is deletes this element, then everything that was after it moves forward. So it has to move forward one by one. So it's going to be, so if you delete at the beginning, it's just going to be O of n because it has to move everything. You get it? But if you delete at the end, then it doesn't have to move anything because there's nothing after the end. So that in that case, it will be O of 1. Okay. Does that answer your question?
Yes.
Okay, so if no one else has any questions, so I'll move to the code example. So here is just an example. So vector int v231, and now I want to see what is v of 1. So v of 0 is going to be 2, v of 1 is 3, v of 2 is 1. Just like array. So v of 1 will output 3. Then I pushed back 5. Then so this vector becomes 2, 3, 1, 5 because they pushed back an element at the end. Push back 4, then this loop I have already shown before. So this will just go over from the beginning and it will print everything that is in the array. So the output will be 2, 3, 1, 5, 4. Then I did v dot pop back, which means I deleted this last element. I deleted from the back. And that means our array is back to being 2, 3, 1, 5. Again, did the same thing. So now you'll get 2, 3, 1, 5 as output. Then here, this right here, last class I introduced a function called sort, and I said that it sorts from iterator 1 to iterator 2 open bracket. Now you see that you have this thing, you have 2, 3, 1, 5, 4, and iterator, the beginning iterator is v dot begin, which is pointing right here, and v dot end is pointing here, and that this close bracket open bracket, which basically means this range is going to get sorted, and that is why v dot end returns a pass the end iterator to like ensure that it is compatible with how sort is defined, and this will sort everything in ascending order. So after this, you will just have 1, 2, 3, 4, 5 in your vector. The next line introduces something called a range-based for loop. So this range-based for loop is basically, it's a convenient way to write a for loop where what you have, instead of writing this whole thing, this range-based for loop handles the iterator behind the scenes for you. So all you have to do is you have to write for loop. Here I've used auto, but you can also put whatever type is here. So you can just write int. You can write int, but if you write auto, the compiler will automatically find out the type for you anyway, as I explained. So auto x is just a name for whatever element we are looking at, and this is the name of the container. Okay. So this loop is the same thing as this loop. This is the same thing as this loop, but is written far more compactly. Okay, it's written far more compactly and much easier way. This is a convenient thing that C++ introduced for us. And now I just output everything. I output x. Okay, so x is basically our star bit. Okay. And the type of this, if you look at it, is going to be int. Okay, it's not the iterator, but it is the value that is pointed to by the iterator, this x. This one right here, again, last class, if you remember, I said that by passing a function called a comparator, this function, if you pass a function called a comparator, it will define a sense of strictly less than for you, right? Now, again, C++ has very helpfully provided with a function that is already there, and that function is called greater int. Okay. I mean, greater actually, this is again a template. So basically greater of some type, which happens to be int here for the vector. So what this does is basically it says that a comes before b if a is less than b. Okay. I mean, sorry, a is greater than b. Okay. So this greater dot int makes sort everything in descending order. So now your vector will look like 5, 4, 3, 2, 1. By default, this comparator function, though we have not written it here, default the default comparator is something called less. And this is your standard definition. A comes before B, if A is less than B. And greater int is A comes before B, is A is greater than B. So this is for greater int for descending order and less int for ascending order. Though you don't need to write less int, because if you don't provide anything, it is assumed by default that you mean less. Okay. So that is basically it for vector. Does anyone have any questions?
Using the sort function, can we like sort only a part of an array? I mean, a vector.
Yeah, you can. Uh, so for example, let's say I wanted to sort from here to here. Okay. So if we look at this from the point of view of iterators, what we have is 2, 3, 1, 5, 4. This is v dot begin. This is begin plus 1. This is begin plus 2. This is begin plus 3. This is begin plus 4. And this is end. So now if we want to sort this range, we want to sort basically begin plus 1 to plus 4 open. I mean, that is the same as 1 plus 3 closed. I mean, I hope you know that. So what we'll just pass to sort is we'll write sort v dot begin plus 1. Remember that we can write this kind of thing because again, the iterators for vectors are random access. So we can move it to any point we want. So v dot begin plus 1 and v dot begin, we'll write plus 4. And this will sort just this range. And then you'll have as your answer, you'll have 2, 1, 3, 5, 4. This part has been sorted. Okay. This is how you sort part of an array, a part of a vector. Got it?
Okay.
Okay. Yeah. You can do the same thing for array also. In array, it's just going to be a little more simple. In array, instead of v dot begin, just the name of the array will suffice, right? So you can just write sort a plus 1, a plus 4 for like C style array. Okay, so let's look at the next data structure. This is a very simple data structure. Oh yeah, so one thing I forgot to mention is vector is found in the vector header. Okay, so if you want to use vector, you'll have to do hash include this thing. You'll have to hash include this thing. For pair, std pair is another data structure. This one is found in this header file called utility. Okay. So pair is a very simple data structure. What it does is just it's in the name. It stores elements as pairs. So A comma B. Okay. So a pair is declared as, there are a few different ways to declare a pair. So you can just write pair int comma int. I mean, basically it's pair uh, data type of 1, and then data type of data type of A and then data type of B, if you want to declare this. So here we are saying A and B are both integers. And next in this one, we are saying A is an integer and B is a double. So here you can have two different types in your pair. You don't need the type of A to be the same as type of B. It can have two different types, like one and like integer and double, 1 and 2.3. You can also have, say, integer and string, so 1 and then hello world. You can have that also. Okay. Now, to access what is there in a pair, there are two things. The first element is accessed using p dot first, and the second element is accessed using p dot second. Pretty obvious stuff. Okay. And there is another third way to make a pair, and that is using this function that is called make pair. So make pair, then you provide what is the values. Okay, so what is the value of A and what is the value of B, and based on that, the compiler, like this So make pair relies on something called automatic template argument substitution. I think it was called. But basically, what it says that it's basically the same as auto. Okay, so it will just deduce what is the type. So if I pass say 2.3, 1, it will automatically say, okay, so this is a double and this is an int. So obviously my pair is going to be of type double comma int. It will automatically do this for you. And then here you can just you don't have to write this whole thing. You can just write auto, because again the compiler will automatically deduce the type for you. You don't have to do it. You don't have to write int double int. Okay. Uh, yeah. So make pair xy returns the pair xy with type pair type of x type of y. Any questions? Okay. I guess no questions. It's a pretty simple structure. And I'll be skipping any examples for this because basically this whole thing is an example in itself. The next thing we'll look at is string. Okay. String is found in a header called string. Well, obviously. The syntax is there are 3 different ways to declare a string. And so you can have, say, you can just declare it. So S1. You can have something like vector. Okay, so this is S2. We are saying S2 has a length of 6 characters, and we are saying that every character is A. So this string is basically A. Again, if you want to have different characters in different places, you can't use this syntax. So if you want to create a string of size S with some character C, you can just use string S2 bracket S comma C. So 6 comma
The
A.
size is without the backslash in for the string.
Yeah, the size is without the
Backslash 0.
backslash. Yeah, backslash 0. It's without the backslash 0.
Okay.
Okay, so and finally there is one more way where you just initialize it when you declare it. So S3 is equals to this string hello world. Okay.
Excuse me.
Yeah.
Can we make that AB means using S2 6 comma let's say AB.
No, you can't.
Okay.
I mean, if you use this kind of syntax, all of your elements have to be equal. Every character has to be equal. You can't do AB. You can't do this. Okay. So again, there are some useful member functions. Uh, Pushback, popback, size or length, empty, begin. All these are already explained in vector, and these few things are basically common to every single data structure. So I'll not be explaining them again and again. Resize, insert, erase. These two are new. Find. So what find does is find returns first position that has given substring. So if you do say s dot find and then you pass say world, okay, s dot find world, then it will return you the position of this thing. It'll just return a position to w. Okay, this find will not return an iterator. Okay, it will not return an iterator. It will return a single integer. Okay, which is the position of this w. In case it does not find a matching substring, it will return something called npos. And to check for it, you have to see like basically you'll have to check uh, if you have if it's equal to string scope resolution npos. So this check basically uh, this means that not found. If these two are equal, it means your substring was not found. Okay, so you cannot just compare it to an integer, you have to compare it to the special thing called npos, and this is how you do it. This final one called substring, this substring returns, well, a substring of the, so if you say s3 dot substring, and so substring, first you have to pass a starting pos, so start, and this is an integer, it is not an iterator, and then you pass length. Okay, so if you say s3, sorry, not substring, substrate. Okay, if you do s3 dot sub str, and you say say 2, and then you specify a length of 3, it will return 0 1 2 3 4. So it will return this length 3 and starting from position 2. Okay, so it will return LLO. And if your length means like the length that you have given ends up exceeding the end of the string, then it will return just the longest part that is possible to return. So if you say s3 dot sub str, say 0 1 2 3 4 5 6 7 8, so if you say 8 and then say 5, so 8 9 10, but then there is nothing after it, it will just return this part, it will return RLT. Okay, and that is basically it. uh, mm, I mean, substring is not used that commonly, but it is useful when you want a part of the string. So instead of writing a for loop, you can just write this function. Okay. So any questions?
Any way to make a string of from index 1 to 9 or 8, something like that?
Sorry, I couldn't hear you properly. Can you repeat?
Okay, means in this hello world,
Yeah,
the one index is E and a ninth index is L.
yeah,
So if I want to make a string up from 1 to n, 1 to 9, can I
yeah.
make it from using any member function?
Using what function?
Any member function.
Yeah. So you can do like string, say string t is equals to s dot sub string, and then you start from 1, and then how many are there? 1 2 3 4
Means,
5.
we have to put the length also. Means I'm asking
Yeah.
about giving two indexes.
No, no, that is not. Yeah, you can't give two indexes. If you use substring, you have to put one. Actually, wait. Yeah, maybe there is a way to do it using indexes, I think. Uh, but I didn't cover that. So instead of writing this, you can do this kind of notation. You can put a curly brace and then write s dot begin plus 1, and then s dot begin plus 9. So this will copy this part of the string to this string.
Yeah.
I didn't cover this syntax, but yeah, you can use this. Actually, you can use this in vector also. If you want to copy part of a vector to another vector, you can use this kind of syntax. I didn't cover it though, but you can read about it. It's there on CPP reference if you want. Yes. So here there are a couple of important things in this example. So here in string, there is an important distinction between using plus equals and just using plus. Like if you do say, there is a difference between doing s plus equals t and doing s equals s plus t. Very important distinction that may cost you a TLE. Okay, so this right here, doing s plus equals this character or string, this is constant complexity or complexity linear in the length of the string you're adding on. Okay, so this is proportional to O of length of t. Okay, this kind of thing means length. Okay, so the reason for this is basically when you're doing plus equals, you are not creating a copy of S anywhere. Okay, so S stays as it is. You're just adding on whatever was in T to S. Okay, but this example right here, this is going to take off S plus T. And that is because when you write S plus T, this is creating a copy of S. Okay, this first creates a copy of S, then it adds T to that copy, and then it copies that copy to S again. So what we have here is, say if S is equals to say ABC, and we have T equals to DEF, then S plus T will first create ABC plus DCF, D plus DEF, and you will get ABCDEF, and then that will be copied back to S. And now you see that initializing this thing will only take O of S, right? And on top of that, you are adding on this thing T, right? So this will take O of S plus T, but in this case, you already have ABC, right? You already have ABC, and now you add T, then you add E, then you add F. So only these characters are being moved from anywhere, like only these are moved from T to S. Okay. But in here, you are moving from S to a copy of S, and then to that copy, you're adding T, and then you're moving that copy again back to S. And the thing about this is, I mean, this introduces a dependency on the length of S. And then if you start using a for loop, you will basically get TLE, because every time you're copying S, so if say S was empty and then you're adding whatever was in S was empty and you're adding whatever was in T to here, it will take first it will be one character, then two character one, then like 0 plus 1, then 1 plus 1, then 2 plus 1, then 3 plus 1, as we are copying 1 because we are copying one character each time, and then 0, 1, 2, 3 is the length of S. So this thing, as you can see, it will just sum up to of n square if you continue up to n. Right. But if you use this kind of syntax, it is only proportional in the length of T. So it will just be 1, 1, 1, 1 up to n times. So this will be O of n. Keep this in mind, because if you use this instead of this, you will definitely get TLE when you are not supposed to. Here I just cleared S, I just removed everything that was in S. So here S was A and here S was AA. And now S is just empty. Then I added the string hello world to S, and now I have a string T called hello universe. S dot size here will output 11 because that's how many characters there are. Wait. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Sorry, S dot size outputs the size along with 0. Yeah, S dot size outputs the size along with this. No, sorry, wait, what am I talking about? Sorry. Uh, sorry, 10 minus 0 plus 1 is 11. So it's okay, it does not include the zero, this delimiting character, the 0. It does not include that. It returns how many characters there are in the string, which is 11. Okay, so 5 plus this space character. And here I am just checking if S is equals to. So to compare two strings, to compare, you can use S equals T, checks for equality. You can use S less than T, you can use S greater than T. Okay. these things you can use to check if two strings are equal, less than, or greater than, lexicographically speaking. Okay, so s is not equals to t, so obviously this will return false. Is s less than t? Again, no, because these two parts are equal, and the first point of difference w is, wait, is u v w. Okay, so s is actually greater than t because at the first point of difference w is greater than u. So if you did this, this would return true. Okay, so to compare, you don't need any functions. You can just use equal, equal, less than, greater than. Okay, to compare two strings. Uh, any questions? Especially, I hope everyone understood this point because this is a very crucial point, and I see people making this mistake all the time.
What's bool alpha?
Oh, bool alpha, it's just a output flag which converts 0, 1 to 2 false.
Okay.
It's not really that important. Yeah, I mean, if you have heard of, say, set precision, it's kind of like that. Instead of like, yeah, it converts 0 and 1 to true and false. Okay, yeah, yeah. I mean, no problems there, I hope. Yeah, okay. So let's look at our next data structure. This is a fairly important data structure. This, along with map, these two data structures are very important and they turn up in problems very frequently. Okay, so we are going to be looking at set and related its related cousin multiset. Okay, so what is a set? So a set, basically, it's in the name. It implements the mathematical notion of what a set is. Okay, so set is basically just if you, okay, so a set stores elements in sorted order, and this and it only has uh, distinct elements. Okay, it only has distinct elements. Multiset, on the other hand, allows distinct elements. So multiset, yes. Set, no. So here I've declared a set. Say I have declared with 11435, but it will not actually contain 11435 because one is repeated. It will only keep one copy of one. So basically, this is going to be 1345. But multiset allows this sorry, shouldn't be distinct, should be non-distinct elements. Multiset allows non-distinct elements, set only has distinct elements. So if you have multiset, you can have two ones, so 1, 1, 3, 4, 5. And the important thing is everything is always in sorted order. Now, you might be wondering how is that possible? Because in a vector, if you insert anything, you will have to sort the whole thing again and again. So that will take a lot of time. So how does it maintain elements in sorted order without causing a massive blow up in time complexity? The secret is that set is implemented internally as a balanced binary search tree. So it's called a balanced binary search tree. This is something you will probably come across in your second year, for those of you first years who are here. And the balanced binary search tree is specifically it's something called a red black tree. So this balanced binary search tree maintains all the elements in such a way that the height of the tree becomes at most logarithmic, log of n. And then if you just want to find anything, you just have to go down in the tree and see its descendants. I mean, we haven't introduced the concept of a tree yet, but you will understand when you see it in graph theory. Okay. Anyway, these details are not really important. What you need to know is that inserting an element takes log of n time. Okay, it's logarithmic, it's not constant. Erasing will also take log of n time. And importantly here, you cannot erase by index. Okay, you have to erase by value only. Okay, or erase by value or erase by iterator. You can get an iterator to the element, and then you can just erase that whatever is pointed to by that iterator. Find is also of log n. Find will return, I mean, I have already explained find, and here also it is the same thing. It returns an iterator to the first element that is equals to your given element. Okay, so if you do, say, if here I do t dot find 4, so it will return an iterator to wherever 4 is. Okay, iterator. And one more very important thing in set and multiset and map is that the iterators are not random access. So iterators not random access. And what this means is that, as in, say, an array or a vector, you cannot jump anywhere. Okay, you have to start at a certain point, and from there you can only move forward or backward, which, since everything is in sorted order, it basically means you can go to the next greater element, or you can go to the previous smaller element. Okay. We will see this in the code example more carefully. Okay. Now, okay, so begin, end, clear, empty, size, these all you have encountered before. Begin will basically start from here, and end will return here. Okay. I mean, internally, again, I need to say that it is not stored like an array like this, it is stored like a tree, but for convenience, you can just imagine it is stored like an array. Okay. So it's like pointing here at the smallest element and ends at the end after the biggest element. And there are two more functions called lower bound and upper bound. Now, you may remember that last class, when we are introducing the STL functions, we already came across these two functions, lower bound and upper bound, and you might ask that why is lower bound and upper bound instead given as separate member function for set and multiset? The reason for that is basically lower bound and upper bound gave logarithmic complexity when we're using them as separate STL functions. But the important assumption there was that the iterators were random access. But in set and multiset and map, the iterators are not random access. So if here you tried using lower bound or upper bound, it will become linear time complexity. Instead, if you use these member functions, you will get log of n complexity. Everything is log of n. Okay. Log n. So if here I said what is t dot lower bound, if I try to find, say, lower bound 2, okay, this will give me 3. I mean, this will give me an iterator to 3. It will give me an iterator to 3. And now if we dereference this iterator using star, we will get 3. Okay. If you use lower bound as a function here, if you write lower bound well, t dot begin and t dot end, and you write 2, this will be O of n complexity because iterator not random access. Okay. So let's just see the code example first. So here I have declared a set. I have declared it like this. Again, note that here it is keeping only the distinct elements, and here we are allowing not distinct elements. This range-based for loop you already know. Now here, this is what I was trying to say, that if you do s dot lower bound and this s dot lower bound, it will be off log n. But this thing is going to be linear because set does not have random access iterators. So keep this in mind. This is a very important point, and I see a lot of people making this mistake. Okay, a lot of people use lower bound the function on a set or multiset or map, and then ask why is my code getting TLE. This is the reason, because set does not have random access iterators. You have to use s dot lower bound. Okay, important point. And then s dot erase, I just erase this element 6. Okay. Any questions up to this point? Okay, I guess not. There is one more important point, and that is in multiset. In multiset, you are allowed to put non-distinct elements, but if you try to erase from a multiset, then you have to be very careful, because if you erase by value, then in multiset erase with value will erase all elements having that value. So if I tried erasing by 1, you would probably think that, okay, so I have 2 ones right here. So after this, I'll have just 1 1. But that is not the case. It will delete all of the ones if you erase by value. Okay. The way to avoid this is you pass an iterator to that element. So here I've used s.begin because 1 is the smallest element I already know. Okay. You pass an iterator and it will delete just what is at that iterator. So s.begin is say here. So it will delete just this one because the iterator points there. It will delete nothing else. So your second one is okay. It will stay. In general, if you want to erase a value x, but if you have say it's non-distinct, if there are multiple copies of s and you want to keep only one of them, in that case, what you can do is s dot erase, and then you say s dot find. Okay, you find an iterator. You like if you do s dot find, then it will return an iterator to the first value that is equal to x. Okay. So you will get an iterator to exactly one value of x, and exactly that value of x will get deleted. All the other occurrences of x are intact. Okay. If you want to erase all of the occurrences of x, then you can just use s dot erase x. Again, this is a very important point. Again, this is like a place where a lot of people make mistakes. Okay. Um, yeah, that's it. Yeah. So any questions about this point? This is log of n, by the way. Okay, yeah. One more important point is that this thing, since it's deleting all of the elements that are equals to x, it is going to be O of log of n plus count x, means the number of elements that equals to x is going to be linear in the count. Okay. I guess no one has any questions then. Okay, so I'll move on to the next one. By the way, I will share some easy problems which are using these data structures after this class. Today only I will share. Okay, so you can take a look through those problems. Uh, okay, so the next thing that we're going to look at is map. Okay, so map. What map is? Map is basically associative array. Associative array. And map is implemented internally the same way as set and multiset as a balanced binary search tree. So again, everything here, this insert erase, lower bound, upper bound, find, these are all O of log n. Okay. So mainly the advantage of these data structures is that you can quickly find elements that are equal to or greater than or strictly greater than whatever you want to find. Size, empty, begin, end, clear, everything I've explained, so no new functions to explain here. Okay, so what a map does is it stores elements as key value pairs. So key value pair. Okay. So you have key, and associated with that key, you have some value. Again, this does not have to be a numerical value. It can be anything. It can be a string, as here. It can be string, it can be vector. Even this key can be a vector, but then comparison time will become like O of n. So it will become like O of n log n to like find. So usually for key, we use numerical values only. But if you want, you can use a vector or you can use string. Just note that the time complexity will then become like linear in the length, because it will take that much time to compare two keys. Uh, yeah, so key value pairs. So here is example of, map. So the syntax of map is uh, map, then data type of the key, and then data type of the value. Okay. So here the key is also integer and the value is also integer. Here we have a double value as the key and we have a string as our value. So one, the key one is associated to the value hello, and similarly for the others. And this is how you can initialize a map, curly braces, and then you just write it as pairs of curly braces. Like this is one pair, this is another pair. Okay. That's how you write a map. How you initialize a map. Okay, so let us look at the code example. Uh, okay, this is kind of a short code example because most of the things I wanted to cover I've already covered in set. But I'll mention one quick use case. But before that, uh, so the way you can insert elements in a map is that you can just write m of x is equals to y. Okay. So what this will do, if if x exists in map, uh, in map, then whatever was the x of value associated with x previously, like say previously x had z, okay, now x will have y. This is what it does. And if x does not exist, if it does not exist, then it will create a new key value pair with having x associated to y. Uh, for numerical values, all of this is O of log n, by the way. Again, I will remind you. And if you are using like if you are not using say, if you're not using numbers, if you're using say strings or vectors, the comparison time is between two keys. Okay. So a map is sorted by its keys. Okay. Uh, so this thing is stored as 1.0, then 2.0, and then 3.0. Not in any other, not like 1.0, 3.0, 2.0. Not in random order. It's always sorted with respect to the key, not with respect to the values. So yeah, so I have demonstrated this here. So m1 equals 3. So 1 did not exist in the map. So now a new key value pair is created. Again, 2 didn't exist in the map. So we have a new key value pair. And then when we try to assign 1 to 6, but 1 was already an existing key in this map. So now the value associated with the key 1 becomes 6 instead of 3. One very fairly common use case of map is say this problem. So problem. You have an array, okay, array of integers, say from 1 less than equals to ai less than equals to 10 to the power 9. Then you have say q questions of the form x, and you have to say how many of X are in A. Okay. So this can be very easily resolved using a map. Okay, so just create a frequency map. Okay, so basically you have int, and this what this has, it has number, and this has count of number. And the way you do this is you write a for loop to go over array A. So for int x in A, and then you do m of x plus plus. So these ints, if they are not initialized previously, they will be initialized to 0, and then you are just incrementing 0 to 1, 1 to 2. And what this will basically do is create a frequency map. So m of x will be incremented as many times as there is x in, if there as many times as there is a value x in A, and then you will basically have count of so x will be become associated with count of x. And now to answer this queries, you just output m of x. That's it. That's all you have to do. And see, map makes this very easy. You could, for example, have sorted the array, and then you could have sort the array and then binary search for first occurrence, last occurrence, and then subtract the distance. But map makes this really very trivial, right? Just one for loop and then just answer the queries in one line.
Could you explain the question like again once this whole thing?
Okay. So let's say you have some array of integers. Okay, one where the entries are in 1 to 10 to the power 9. Okay, and now you have some questions in which you ask how many of a certain number are in A. So A can be like say equals to 2 to 10 to the power 9, 10 to the power 9, 102. And then I ask you, say, how many uh, how many twos, how many 1E9s, how many sixes, how many tens, how many 102s. And I can ask you this a lot of times, 10 to the power 5. Okay. So basically what map does is it creates a histogram kind of. So a frequency array, you know what a histogram is, right? So x is mapped to the number of occurrences of x. So 2 is mapped to 2, 1E9 is mapped to 2, and 102 is mapped to 1. Their counts. And now if you want to answer how many 2's there are, you just output m2, which is equals to 2. You output m102, which is 1. And say if you try to check for m6, m6 is not there. So it is initialized to 0. So you'll have a key value pair like 60, and then your output will be 0. Got it?
Okay.
So we are almost out of time, but I have a few more things to show. So I hope you don't mind if I extend the class by 5 minutes or so. Okay, so next we'll look at a couple of very simple data structures, which just makes life a little bit easier, though honestly they can both be replaced by double-ended queue. So the data structures are stack. So first we look at stack, which is in header file stack. And well, I guess all of you know what a stack is. It basically it's just imagine a stack of books, and you're just removing books from the top of the stack, and you're putting books on top of the stack. So it is what is known as a first in first out structure, FIFO. First uh, uh, first in, first out. So the first thing that wait, first in, sorry, it's actually
Last in, first out.
Last
yes,
out.
I'm sorry. Last in, first out. Last in, first out. So the last thing that gets put on top of the stack is the first thing that is pulled out of the stack, right? So stack does not have any iterators, as I mentioned in last class. All you can see is you can, okay, so you can push things on top of the stack. Okay, so if you have a stack, you can push 1, you can push 3, all from the top of the stack. You can pop from the top of the stack. You can remove this 3. Then you can remove this 1. Okay. And you can look at what is the topmost element of the stack. So if you did st.top on this, you would get 3. Right? If you did st.top. Size and empty, So stack is very simple. I hope it does not require much explanation. Push, pop, and what is the topmost element of the stack. An example use case is this program, which is just balanced bracket sequence parsing. This balanced bracket sequence is something that comes up sometimes in problems. So balanced bracket sequence basically means that every opening bracket is matched with another closing bracket. Okay. So we have this string here, which is a bracket sequence, and with stack, what we do? So the logic is that basically whenever there is an opening bracket, we can push it into the stack. Whenever there is a closing bracket, we can just remove the topmost opening bracket from the stack, right? Because then we know it is matched. If it is matched, we can just remove that from consideration. And then if we have, say, a closing bracket, but it is empty, that means this closing bracket is not matched to any opening bracket. And then we can just say it fails. And at the end, if we have any remaining open brackets, then that is also a fail condition because these opening brackets were not matched with any closing brackets. Okay, so again, you can do this with a vector. Let's say you can just push back, pop back, but it's just for convenience, this stack. I didn't write this particular fail condition here, so if it should be here, if stack is not empty, then cout fail. But you get the idea behind this, right? There is, I think, a ZCO problem, which is basically just this. I'll give a link to it. You can just try out using stack for that problem. Okay, basically this problem only. So any questions? Do you want me to like explain stack or explain the logic of this balanced bracket sequence again? Okay, I guess no questions. We are out. Yeah, okay. Yeah.
I have another question, means
Yeah.
related to this, but not this.
Okay. What is the question?
Means, I want to find the maximum balanced sequence. Means I found a question on code forces, I think. Means for this thing, like I can have the maximum balanced expression from second index to last, like that. Means, am I clear?
Not exactly. Can you like
Okay, I will, means can I message you in chat?
yeah, you can share the link of that question in chat. I am kind of pressed for time right now, so I will answer your question after I'm done, if that's okay.
Okay.
Uh, okay, so just two more are left, queue and double-ended queue. So queue, again, very simple. You know what a queue is. Queue for a bus, let's say. People enter from the back and exit from the front. So this one is a FIFO structure. First in is first out. Right. Because first person to enter queue is the first person to enter the bus. Okay, and this is implemented like this, and this one has push, pop, size, empty, and this one has two functions called front and back. So front is basically whoever is at the front of the queue, which is the oldest element, oldest, and the back of the queue, whoever entered last in the queue, so newest. Okay, this is queue. the code example of a queue is just this code snippet of breadth first search. This is called BFS, breadth first search, and this algorithm basically traverses a graph according to like it traverses all the neighbors. Okay. Instead of going by children, it goes by neighbors. So a detailed explanation of this algorithm will be in your graph theory class. I will not explain it here, but this is just presenting a use case of queue. Okay. And the last one is double-ended queue. Double-ended queue is very similar to vector, except it allows this right here. It allows constant time insertion and deletion from back as well as front. So it's like a double-ended queue, means people can enter and exit from the front, people can enter and exit from the back in constant time. Okay. In vector, you do not have constant time here. It is it is linear time at the front, if you remember. And all the functions are basically the same. So I am not giving any code example for double-ended queue. It's basically very similar to vector. Okay. One important thing is that in the double-ended queue, internally, everything is not stored contiguously. It's not stored like an array as in vector. It may be stored like this. But that distinction is not very important to us. Okay. And that is basically that is the end of the class. And here are some links where you can read more about iterators. Okay. I shared the link for all the containers in the last class's slide, which I will share after the class. Okay, I'll combine these slides and share. Okay. So yeah, that is, yeah.
Will you provide the slides of today's class?
Yeah. I will share it today only. I'll share it today only. I'll combine these slides and share with the previous class. Okay. Okay, so this is the end. If you want, you can leave. Class is over. And whoever asked that question, so yeah, you can paste a link in chat, I guess. So who was asking that question about bracket sequence? Yeah. So you shared the link in chat.
No,
Class is
it
over
is a
by the
code shape, I think. I have to check it.
I had a doubt in number theory.
Anubhav?
Yeah. Okay.
Actually, in the last fortnight, there was a question in which we needed to find some a value 2 to the power a. While calculating a, that was also quite large, so we need to use mod in that too. So how to do that?
Yeah, so you tell me. So you remember the Fermat's little theorem, right?
Yeah.
Yeah. So what happens is after you so you remember that the modulo given was probably 10 to the 9 plus 7, right?
Yeah.
Okay. So as said, 10 to the 9 plus 7 is a prime number. So what happens is whenever this number, like your exponent, let's say you want 2 to the power m, small m. Now, whenever this number m starts from, let's say you increase this number m from 1 to, let's say, a very large value. So it goes like 1, 2, 3 up to, let's say, 1e9 plus 1, 1e9 plus 2, and as it hits 1e9 plus 6, your the value of 2 to the power m gets 0. So after that, let's say when it goes to 10 to the 9 plus, let's say 11, then shouldn't it be equal to 10 to the 9 plus 11 minus 10 to the 9 plus 6 whole on top of 2? Something like that.
Sorry, you told 1e9 plus 6.
1e9 plus, so you want to find a number like 2 to the 1e9 plus 11, let's say. Okay.
Okay.
So 1e9 plus 11th power of 2. Now you know that 1e9 plus 6th power of 2 is equal to 1. Then what do you do?
Yeah, I see. Means while calculating the a, we need to take modulo with mod minus 1.
Exactly. So when you are exceeding mod minus 1, you can take the modulo with respect to mod minus 1 of the exponent and still have the same value of 2 to the power that thing, modulo the final mod. So now
Okay,
are things
understood.
clear?
Yes, sir.
Okay, so do try to get an AC on that question. It was a good question, I guess. Okay, so was I able to clear your doubt?
Yeah, I understood.
Okay. Okay, so I think I can stop the recording. Mainak, should I record the discussion on the parenthesis question?
No, no need for that.
Okay.
This question right here.
Yeah,
You remember